Hello, everybody, and welcome to this guest lecture in Geography 338, Remote Sensing. In this video, we're going to be focusing on light detection and ranging, or otherwise known as LiDAR, what it is, how it's collected, and what we can do with it. For those of you who don't know, I'm Dr. Zach Hilgendorf. I am a Wisconsin native, grew up in Reedsburg, Wisconsin, got my bachelor's here at the University of Wisconsin-Eau Claire in environmental geography back in 2015. Got my master's studying with another former Blue Gold, Minnesota State University Mankato in 2018. My PhD just this past year in 2022 at Arizona State University. I'm back. For those of you who haven't met me yet, I've been around the department. I'm a physical geographer and a geomorphologist. And you might be wondering, if you do know who I am or don't know who I am, who's this random dude lecturing at us today? Well, I have been a longtime lover and user of LiDAR data sets. On that image next to me right there on the side there underneath my talking face, that is me on a beach in Northern California operating a terrestrial laser scanner, a ground-based LiDAR system. I used this throughout my PhD for 4 straight years. I got to know these systems very well, have been processing this data since I was an undergraduate at Eau Claire. So I've got a lot of history working on this type of stuff and a lot of passion for it. LiDAR is one of those things that really excites me and gets me going as far as nerd loves go. So sit back, enjoy, and I hope you learn a lot in this lecture. So let's go ahead and get started. So first off, what is LiDAR? Well, LiDAR stands for light detection and ranging. LiDAR is what we call an active sensor. Now in remote sensing and in the past number of weeks, you've been learning about things from passive sensors. Passive sensors just mean that it is using something else. It's requiring emitted radiation or reflected light off of different surfaces. LiDAR is an active sensor. It generates its own light source in the form of a laser pulse. That means you can use it in day or night. Here we can see an example of what a passive on the left or an active on the right sensor does. A passive sensor is just detecting what's emitted from the landscape or reflected from another source, like the light of the sun, for example. An active sensor emits its own signal, and then the sensor measures what's reflected back. Sonar, radar, and LiDAR are kind of quintessential examples of an active sensor. So basically what it does is it takes the range or the distance of a reflecting object based on the time it takes for that emitted pulse to return back to the sensor. You can see that plane on the left there. That's an aerial LiDAR system or an example of one. You can see that clock ticking away. It's measuring in light seconds because this pulse is a form of emitted light. It travels at the speed of light. We'll get into that here in a little bit. But what we're doing is essentially trying to reconstruct the surface by using this pulse. So whether that's buildings on the surface, the bare earth itself, vegetation, etc., it gives us the ability to process and quantify these things based off the time it takes for that pulse to send out and come back. There are many different forms. There's terrestrial or TLS, terrestrial laser system. There's aerial LiDAR or aerial laser systems, ALS. You can see that in the middle there. And then there's underwater or bathymetric. So each of those is a little bit of a different setup. Now, terrestrial there, you saw in that first image that I showed of myself, that was a terrestrial system that was stationary. So I had to move that around and set it up and kind of figure out my own sampling strategy and schema. You see on the bottom there, mobile is another form of kind of terrestrial. It's ground-based. So the things that are running automatic cars that are trying to figure out their way. Heck, even our little Kiwis on campus, I believe, use a form of LiDAR to figure out where they are and what's around them. It's on the Apple iPhones these days. You can use LiDAR in terrestrial form in a myriad of different ways. Aerial is what I would consider our conventional LiDAR. That's been around the longest for the most part. We've been using that for county-based LiDAR flights, and that's typically what we see if you've used any LiDAR from Eau Claire or Chippewa County or Pepin or anything like that. Underwater uses a different type of laser, and we'll get into that here in a little bit. So while terrestrial and aerial use kind of the near-infrared spectrum of light, in the underwater or bathymetric, we're actually using a green laser. So we'll get into that here in a little while. And then we have single versus multiple return potential. So what this does, in a lot of ways, it allows us to separate features on the surface from our bare earth. That's the big goal. Strip away everything and see what just the ground looks like. And that's a lot of what LiDAR is used for. So if we see here on this image, this is kind of a typical view of a multi-return LiDAR system. So the laser pulse is emitted from the top, and you can see where our first return is, the point where it strikes the top of that tree. Maybe it missed the leaves and the branches above it, but it hit that part and it bounced back. And then it only reflected a portion of that laser back. So if we're thinking of it like, a circle, only a part of that hit the leaf and bounced back. The other part, for example, maybe went through and maybe encountered another leaf, and then that part was reflected back, and then so on and so forth until you hit the ground, that last return. And based off of that signal strength and how much of the signal returns, that's how we know what types of surfaces we've hit, the elevation or range really that they struck, because we don't get elevation until we kind of correct it to our ground-based systems, which we'll talk about here in a little bit. But this is a way to kind of understand and reconstruct not just our ground. So if we were using, for example, a single return or discrete return LiDAR, basically what we get is what we get. It hits something, it bounces back, we're reconstructing that surface. A multi-return, sometimes called a full waveform in some cases, multi-returns allow us to see further in and allow us to see different portions of that signal and the intensity and the strength at which that signal returns. And then LiDAR is optical. And that's a really, really important aspect of LiDAR. Everything in the direct line of sight is seen by the scanner. If it's not in the direct line of sight, it isn't seen. So let's see what that looks like here. So this is a terrestrial laser scan of a forested region. And you see the kind of the general elevation gradient. So like the lighter greens to the whites, that's looking at lighter greens being the ground level, the whites being up on the trees. And notice all of these kind of big, long black zones. What those black zones are is shadow zones. So the terrestrial laser system, which is right in the middle where that circle is, has a few blind spots. The first blind spot is immediately below it because it doesn't see in full 360 degrees front to back. It only does that as it spins around in a circle or side to side. So there's a shadow zone underneath the TLS system in this case, or if you were flying an aerial LiDAR and you hit woody debris, you aren't able to penetrate that. Or if you hit a building, you're not able to penetrate the ceilings or the walls of that building. So those actually function as shadow zones. And you can see here those long features that I've highlighted striking out to the left and right of the image. Those are shadow zones where there's a big tree in the way. And then behind it, as that pulse kind of, we think of it spreading out, as the pulse spreads out, more and more is shadowed behind whatever function or whatever feature was kind of covering it. What LiDAR is not, it is not all weather. Rain, snow, fog, etc. are problematic. Basically what happens, and this is from firsthand experience, if I was to use a terrestrial laser scanner or anything like that, and it was really foggy, what it would basically look like is a sphere of points immediately around the scanner because it's reflecting off of these particles, these fog particles and water particles and droplets in the air, and it's going right back. So you basically lose that signal because it's already bouncing off of something. So you have very poor returns. Same if it's snowing, if it's rainy, etc. If it's hazy, there are going to be problems. It is able to, or it's not able to see through features, as we said before. It's optical. If there's a wall or a tree in front of you, you're not going to see on the other side of it. So you have to accommodate that, and you have to build that into whatever your sampling strategy is, or you have to accept that you're going to be unable to see some features within the landscape. And it's not a substitute for photography. While some LiDAR is flown concurrently with orthomosaic imagery or high resolution imagery, or perhaps your terrestrial laser scanner is equipped with a mounted camera, which you can use to color your point clouds, it's not a substitute for imagery. And that's just something we have to accept. The main purpose here is that range data. So we want to figure out where something is on the surface of the planet, its elevation, its distribution, etc. That's where LiDAR excels. It is not a photogrammetry tool. It is not a photography tool. So how does LiDAR work? Well, simply, a pulse of light is emitted at a precise time is recorded. The reflection and angle of that return pulse is detected, and the precise time is recorded again. We know the length of time it takes for that pulse to go out and come back. Using the constant speed of light, roughly 3 times 10 to the 5th kilometers per second, that delay can be converted into what we call a slant range. Basically, we're trying to figure out the strength, angle, and distance of that return. Knowing the position and orientation of the sensor are XYZ, or as my Canadian advisor used to say, XYZ. If you see Dr. Joel, make sure you use the Z word. The XYZ coordinates of the reflective surface can be calculated. That can give us, in some cases, up to 200,000 pulses per second. And in some of these systems, for example, terrestrial based, it takes 30 seconds for that scan to spin around. So let's do the quick math there. You're looking at 6 million points or so per scan. It's a lot of points. It's a very dense array of points that we have to figure out how to work with. As we said, it's optical. Everything in the direct line of sight is seen by the scanner. If you want to see more, you either have to move that scanner or have another pass where you're seeing different aspects at different angles. So discrete pulse versus full waveform is what we talked about before. Discrete pulse is basically a binary yes or no return. Only the location of that return is saved. Full waveform is what we call digital backscatter waveform. It saves the entire energy spectrum of that return. So if you look at that image on the right there, you're looking at the intensity of that outgoing laser pulse, and the return waveform is being created as it goes through the crown of that tree, as it's encountering things in the understory, and it's hitting the ground. So you're seeing these kind of pulses as you go down through different encountered features. Now the difference there is if you were to use discrete, the data size is going to be a whole lot smaller. Your processing time is going to be a whole lot smaller, and it might be a lot more easy to work with. But if you need that data and you want that full waveform return, that's the way to go. So it's really just kind of a preference in what you need or what you have available to you kind of thing. So LiDAR structure return, or return structure, pardon me. This was taken from a really nice presentation from Chris Crosby at UNAVCO, kind of one of the geodetic and geodesy surveys and organizations here in the United States. On the left is the point cloud view of the tree on the right, and each point is colored by the return it came with. So red is the first return. It's the first time striking that feature and bouncing back. Yellow is the second return. So same pulse, but it's been attenuated. It's lost some of that. It's bouncing back. And the green is the third one. So again, if we're thinking of like a slice of a pie, that's the last slice that hasn't been eaten when the other 2 slices have already been eaten. So it bounces back. That's the final return. That's our third return, or our last return in this case, is the ground surface, usually. So if we think of LiDAR, it's coming from a laser return, right? That's what we've talked about. So there are 2 different forms. There's the green light, which is right around 532 nanometers, and near infrared, right around 1064 or so nanometers. So basically what we're looking at is green light is what we would use in bathymetry or underwater LiDAR. The near infrared spectrum, or right around that 1064 nanometers, is what we would use if we were trying to use aerial or terrestrial LiDAR, because we're just looking at the surface. We're not trying to go through the water. If you're using a terrestrial or aerial system, that basically that entire signal is going to be absorbed by the water, and you're not going to get anything back. So you lose that signal whenever you're over water, because water is really good at absorbing that wavelength. If you use a green light, you're going to be able to penetrate down through the water column and actually be able to see the surface below. So you just have to understand what you're going for. If you're going for something in the that's just, you know, a prairie or a forest or a beach, you just have to make sure that the LiDAR that you want or that you're using is one that's going to give you the return that you need. If you're trying to look at, you know, subsurface data over a lake, you're not going to get it with a near-infrared laser system. You need that green light system. So LiDAR data quality. Not all LiDAR is created equal. There's a huge range in quality, resolution, and accuracy of data publicly available. Typical metric is pulse density per shot spacing. Basically, what we're looking at is the density of points per meter, for example, describes the sampling density of data and the potential grid resolution. Shot density is highly heterogeneous. Ground point density is typically far lower than the total point or pulse density. And we typically evaluate LiDAR data quality by testing it against ground control, like GNSS systems or other things that are operating continuously, looking at big images and quantifying swath-to-swath reproducibility. So as you're flying back and forth, for example, making sure that the data sets you've collected are lining up the right way. And then we can read the metadata and survey reports to kind of get a better idea of what those error or uncertainty estimates should be. And that's something that I highly recommend doing is if you're going to use LiDAR, understand the uncertainty that comes with it. And you can find that in the survey and metadata reports very, very easily. So looking at LiDAR data error sources, there are two major sources of uncertainty: geolocation and vegetation and terrain. So basically we're looking at how well can we reconstruct the surface based off of our GNSS data. So how well do we know where we are? How well can we process that data? And where does our processing uncertainty come from? Because you're not going to perfectly be able to line up every single point. There's uncertainty there. And then vegetation and terrain can exacerbate those issues. If you have a heavily vegetated surface, that laser is not going to always get down to the bottom. So your bare earth that you might be trying to get at might not be rendered correctly. Terrain, if you have a very steep slope, you're going to see uncertainty there because you might have areas that aren't being captured by the laser because that slope is maybe oversteepened. So you have to understand where these sources of uncertainty come from to really be able to talk to how accurate the data product that you're trying to produce is. So if we look at overall accuracy, for example, if we were to use spaceborne LiDAR, we should have four systems here: spaceborne, high altitude, airborne, and terrestrial. Spaceborne, the altitude is flown at about 600 kilometers. We have about a 60 meter footprint, and our vertical accuracy is between 15 centimeters and 10 meters, depending on the slope. High altitude LiDAR flown right around 10 kilometers. We have a horizontal footprint of about 15 meters, so 15 meter resolution. And our vertical accuracy is between 50 to 100 centimeters. Now, if you have bare ground versus vegetation, if you're bare ground, you're towards that 50 centimeters. If you're vegetated, you're towards the 100. Airborne LiDAR, so aerial LiDAR or ALS, is flown around 1 kilometer in height. The footprint is much better. It's about 25 centimeters in a lot of conventional or contemporary aerial LiDAR. And then the vertical accuracy there, I have it listed at 20 centimeters. It can be lower than that, but it's often an industry standard is about 15 centimeters is what most people will list as their accuracy or vertical uncertainty for their LiDAR. So just have to take that into account if you're trying to do air budgeting. And then terrestrial, it's at about a meter. Typically the scanner is right around, head level. So 1 to 2 meters in altitude, if you want to say that, or off the ground level. The footprint, it can be a centimeter, it can be 10 centimeters, depending on how much you coarsen your data. Honestly, unless you're doing very, very high resolution vegetation analysis, I've coarsened all of mine to 10 centimeters because if you think about it, about that much, unless you're doing things where you need to see leaves, 10 centimeters is just fine. And then the vertical accuracy can be as low as a centimeter, it can be as high as 10 centimeters. It's highly variable depending on the surface, what's covering the surface, etc. And what are our primary deliverables? Well, a point cloud is one of them. That's really the bread and butter of LiDAR systems. The fundamental LiDAR data set is our point cloud. Discrete XYZ points with attributes: intensity, return number, number of returns, total, classification, GPS time, RGB, etc. This is our elevation data. This is the range data that we want when we get LiDAR. What we see here, this is from one of my point clouds. This is a beach and dune system in Northern California, right above, well, would that be here? Right there. That is a small little shrub growing on the upper portion of the beach below the dune. And I have this colored by elevation, so it's a few meters high at the very top there. So maybe 3 or 4 or 5 meters high from the bottom to the top. And you can see up top, that's all vegetation that you're seeing. And I haven't stripped this one. I just wanted to show the points in all of their glory. So you can see things like footprints, ripple marks, vegetation, grass. You can see so many different things in these point clouds that are incredibly useful if you're trying to do things like volumetric calculations or biomass calculations. So this is a video from a good colleague of mine, Mike Grillo, formerly of UVic, or University of Victoria. Now he is with the RAPID team at the University of Washington. He basically goes out on the onset or right after a natural disaster, and he will go and survey that in with LiDAR systems. Really fascinating stuff that he does. I will play that one more time here. So this is just a flyover of the point cloud from October 2015 of this beach that he was looking at in Northern California, showing some erosion happening on the beach face. Another primary LiDAR deliverable is a hydro-enforced DEM, or digital elevation model. DEMs are really what we want. We want elevation models. And a DEM is different than a DTM, or digital terrain model, or a DSM, digital surface model. Depending on whether you're American or European, there's some preferences on which term to use. I prefer DSM, or digital surface model, to basically reference or refer to all of the points in their entirety that have been rendered into a raster surface. So that includes vegetation, buildings, logs, etc., and the bare ground, where I use DEM to refer to just the bare ground itself, where the Europeans and others typically tend to refer to digital terrain model, or DTM, as being the surface that is reconstructed with all the points involved, and DEM, we still use the same there. So a hydro-enforced DEM, basically here, this aerial LiDAR flight went over, and you might notice something. I'll draw here with my pen. Grab red here. There's a stream that's running here. But this bridge is in the way, right? So if this stream is coming down and flowing this way, and you're trying to reconstruct the flow of that stream, which is a really vital use of LiDAR, this entire area on the upstream side is going to act as a pond. So this entire thing here is going to fill up, and then it might spill over the lowest point, which seems to be maybe over here. So it would spill over it, but that's not actually what's going on. We know that that stream is flowing underneath the road. So hydro conditioning or hydro enforcing basically says, okay, we know this is a road, and to accurately flow, we're going to cut right through that road and act as though the stream was flowing through it. And that this was basically, it's just what we call stream burning, or hydro enforcing, hydro conditioning. We're basically just taking this road and cutting right through it with our stream. So that when you're trying to do flow reconstruction, the stream is flowing the direction that it needs to go. Break lines are another thing that we generate here. So break lines basically mean that there's a surface here that is very poorly reconstructed, very low point density, whether that be a pond, lake, river. Oftentimes it's a water-based feature. And break lines are what's generated on the edge of those, so that what you'll have is like a consistent surface that's generated within this, so it doesn't do anything wonky to your DEMs. Other deliverables, we can get classified point clouds. So you can really do anything you want with a LiDAR point cloud. You can classify it into things like ground, low, high, medium vegetation, buildings, water, error points, blunders, etc. You can look at the intensity, return number, number of returns, GPS time, RBG or RGB values. You can tile or swath into LAS or LAZ. LAZ is the compressed form of LAS, which is your typical LiDAR file type, is an LAS file. our raster data derivatives. We've got our DTMs, our DEMs. Again, there's that distinction there. Hill shades of those, intensity maps, RGB readouts, tiled geotiffs, IMG, which is ERDAS Imagine, which I believe you all should be using in the course. ARC binary files, kind of really anything that you want. And anything that you can imagine. I have, anytime I get a LiDAR data set, I end up with about 10 different feature raster surfaces that I'll create off of it. I will create a digital elevation model, a digital surface model, a slope percent, and a slope degree, hill shade, a point density is another one that I'm very interested in. So how, when we have our raw LiDAR, how many points are in a certain area. I'll show one of those here in a little bit. I do things like vegetation height. So basically I'll take our digital surface model and our digital elevation model and subtract the two. And wherever it's 0, I just kind of remove that because that means it was just bare ground once and it was bare ground again. So I will basically create a vegetation height raster so I can do things like calculate biomass on the surface. There's really no shortage of things that I do with LiDAR at this point. And that's because there's no shortage of things you can do with LiDAR. So let's dive into some of the specifics here. So aerial LiDAR specifications, this is mostly what you're going to use. It's not always easy to get terrestrial LiDAR data sets. I will provide some really phenomenal resources at the end of the video here to show where you can get some of those data sets. But let's first talk about aerial LiDAR specs. So there's a few different system components. We've got our aircraft. This is the thing flying around. We have our scanning laser emitter receiver unit. So basically the thing that's sending out and receiving the pulse. Differentially corrected GPS system. So there's a GPS reference station on the ground. There's one on the plane as well. And what we're basically doing is correcting where the plane is flying to where the GPS says it is. And a lot of times we bring in what's called the continuously operating reference system, or CORS network as well. And that is a continuously operating system of GNSS systems across the country. So we know with very high degree of accuracy where those laser points are, and we need to so that we can reconstruct that surface accurately. It has an IMU, or an inertial measurement unit, on it. So as that plane is not flying sturdy as a rock. It's getting hit by things like turbulence, air pockets, etc. So what the IMU does is it's saying, okay, I know the roll, pitch, and yaw of the plane. So whether it's nose down, slightly tilted, back, whatever it is, it's able to account for that and correct those lasers to where they need to be. And then there's a computer running the show behind the scenes. So this is kind of what a typical aerial system looks like. Now, that's not all, because there are different ways to basically send out that pulse. There are different scanning mechanisms. So there's an oscillating mirror, which you can see on the top, a rotating polygon, and a nutating mirror, or a Palmer scan. So basically what we're seeing here is just different ways to collect that pulse and send it out. So most common is that oscillating mirror. What you get is this Z-shaped sinusoidal return. It's most common pattern that we use. Some of the really famous, really prominent LiDAR manufacturers out there, like Leica and Optech, and probably Regal as well, use this exact mirror setup. So this oscillating mirror. The rotating polygon, again, it's just another way to send out that laser pulse. Basically here what you get are these parallel line returns. And then the Palmer scan is you get this elliptical return. You can kind of see that circular return coming back to the laser. Determinants of LiDAR data characteristics. It's a combination of a bunch of things. The scanner system and the beam pattern, how that beam is sent out and comes back. The flight altitude, pulse rate, so how quick and how rapidly new pulses are being sent out and returning. The scan frequency, the scan angle, so that means the possible degree of return is only around 30 degrees, so anything past that, you're not going to get a return. And then the scan swath, so how wide that scan is trying to go horizontally on the ground. So, and you can see on this image here, canopy penetration gets worse with increasing scan angles. So if you got a really big scan angle, you're not going to penetrate that canopy like you would if you had a nadir directly down 90-degree shot. The LiDAR data characteristics here, raw return data as XYZ points, high spatial resolution. You typically get laser footprints of less than or equal to about half a meter. Typical densities between half to 20 pulses per square meter, 2 to 3 return pulses in forested areas, and your surface canopy models typically grid out to about 1 to 5 meters. Large volume of data, absolutely. 5,000 to 60,000 pulses per hectare, 10 to 100 plus thousand returns per hectare, and about 0.4 to 5.4 plus megabytes per hectare. So this gets big really quick. We've got our return density here. So in LiDAR, the footprint size decreases with increasing post spacing. And importantly, the last return from a discrete return system is not always the ground, and that's really important to remember. LiDAR sensor systems vary in the number of returns from a surface. So here you can see the first return. If we look, it's a little bit tough to see, so I apologize. That first return is completely, almost ubiquitous, full cover across the entire surface. The second return, the stuff that's penetrating through, is much, much less. And then if you look at that third return, that what is typically looked at as hopefully our ground, much sparser in these really heavily vegetated areas, especially from these aerial LiDAR systems. It depends on reflectivity. So highly reflective objects may saturate some laser detectors, while the return signal from low reflectivity objects may be occasionally too weak to be registered as valid. Think of albedo, right? If we should have learned the term albedo, so the reflectivity of a surface. Snow, highly reflective. Deciduous trees, moderately reflective, about 60% reflectivity at a wavelength of about 900 nanometers. Beach sands, 50% reflectivity. Concrete, 24%. Lava, 8%. Black rubber tire walls, 2%. So this is how reflective that surface is. So if you have lava or a black rubber tire wall, these things might be absorbing your laser, whereas snow might be reflecting it a little too well. A strong sunlight reflection off of a highly reflective target may saturate a receiver, producing an invalid or less accurate reading. That's important to note. So just have to think about what the surface looks like that you're trying to reconstruct as you're looking at and trying to use this LiDAR. Dust and vapor, as we alluded to before, can weaken and mess with your laser scanning. Using a last pulse measurement can reduce or eliminate this interference, but it's not always perfect. Systems are expected to work in such conditions regularly can be optimized for these environments. It just depends on what you have. That's, I think, the big crux here is if you're regularly working at somewhere that's hazy or there's a lot of blowing material in the air, whether that be sand or snow or water, you just have to accommodate that and work with that and understand that your product is going to be impacted by whatever the systems or whatever typical trends you're seeing when you're trying to collect the data. Background noise and radiation. The LiDAR or the laser is not affected by background noise. Most systems determine baseline radiation levels to ensure that it doesn't interfere with measurements. It's just something to note. So aerial LiDAR is awesome. It lets us go from something like this to something like that. And that's really great, but it's not the greatest. Aerial LiDAR I used for years and I still use it all the time. I love aerial LiDAR. I have been spoiled because I get to play with terrestrial LiDAR. So if you think about, we were talking about pulse rates of roughly a half to 20 points per square meter. I get to play with things that are like 282 pulses per 10 centimeters or 1/10 of a meter. This is what I get to play with. These are this is a terrestrial LiDAR scan of a beach that I did. And what we're looking at is point density per 10 square meter or 10 square centimeters. So 10 centimeter by 10 centimeters square. And this is what I coarse in my data to, so that's why I'm interested here. So a couple things you might note is look at all those red circles, and then right underneath of it is this weird hexagon, right? That's exactly what I'm talking about, where we have a shadow zone underneath. So if we were looking at, maybe I'll turn it to white here. If we were looking at this scan right here, notice all that red, but there's green there. So we are seeing, somewhere in the neighborhood of, 20, 30 per 10 square centimeters. But that's because I'm seeing it from this position, all of these positions here. So basically I'm highlighting every location that I took a scan from that would have seen that exact point. So all the way over to here. So it's those surfaces, it's those scans that are able to reconstruct that area underneath where my scan was at that exact position, and vice versa. So you have, if we look here, I don't have exactly on here where those scan locations were, but you can see them pretty well all throughout here. As I'm drawing these kind of in just to show you where some of these scan positions were. This is an interesting area because it's incredibly densely vegetated. So we don't see a lot of returns when I remove all the vegetation and we're left with a bare earth model. We don't see a lot of good returns here because it's such a dense, nasty array of kind of continuous vegetation cover. So the steps here to go from a digital surface model to a digital elevation model to a 10-centimeter rasterized point cloud. Basically, you start with your unfiltered point cloud and you remove all the spurious points. I've seen perfectly rendered birds in the sky that were flying by when my laser scanner was running. Things like wood that I don't want in my digital elevation model have to be removed. Vegetation has to be removed. Once all that's done, I can rasterize my points. So if you look at, if we look to the bottom left there, so for this study site, if we're looking at the full size of the site, roughly 7,254 square meters, the digital surface model point cloud was roughly about 48 million points for what I was looking at here. The digital elevation model point cloud was roughly 41 million points. And my decimated point cloud was only about 6 million points. So you're kind of looking here, we're slowly stepping down and losing points as we're filtering things out. Here, this is a really cool one. This is a 3D rendering of this beach dune system. The green is vegetation. So we're seeing here how the beach is changing, the dune is changing, how the vegetation is growing from here, November 2015 through September of 2019. At this site, we're still going. Last time I was out there taking a laser scan of this beach was July of 2022. And terrestrial LiDAR is so much more beneficial than things like photogrammetry in some ways. So in this case, the top 2 point clouds are a photogrammetry surface that I created. So I flew a drone and I created a surface based off of the drone data that I had. The bottom is a terrestrial laser scanner. On that, if you look at the top, for example, if we look right here, there's one of those bushes that I pointed out way back when, and it just kind of looks like a bump, a mound, right? Whereas here, you can actually see leaves within that vegetation. Once you remove it, here you're left with this big gaping hole, whereas here we're actually able to reconstruct some of the bare ground underneath those leaves, so we're actually able to keep that, and we don't have loss of error or a loss of elevation leading to error in our point cloud estimates. Just to point it out up here, you can actually see blades of grass here that isn't captured in the UAS or the drone point cloud that was created during the exact same time. These were flown within hours of one another. So some potential applications. There is the experimental application. So a very good friend of mine, Madeline Kelly, who's currently finishing up her PhD, was doing some wind tunnel studies, and we wanted to see how ripple patterns were changing as this system was running. This is as the wind tunnel was working for 5-10 minutes or so, it would generate ripples and these patterns, and we were trying to figure out the spacing of those ripples, how they were forming, how they were moving, and we used the laser scanner to do that. You can see that scanner right here. That was the same one that was operating on that beach, pointing up, focusing here at this portion of the wind tunnel. If we look at the point cloud on the side, it was positioned right where I'm drawing my circle right now. So we would take a scan looking this way, and then we would move it to the other side of the tunnel and take the scan facing down the tunnel. So we were able to accurately reconstruct those point clouds. Here you can see this is before, this is right as we started, what it looked like. And here it is after it had been working for a while. So we're actually able to see these ripples develop. We can measure these. We can look at slopes. We can look at changes in surface elevation, kind of really accurately understand how these ripples are forming and changing. And Ms. Kelly is doing some phenomenal work. And these data sets will come out eventually in some papers that she is working on that I hopefully will be able to help her out with. Other potential applications, this is kind of my bread and butter. What I do is change detection. So I take two surfaces. So we see here on this right, October of 2018 and May of 2018. So a newer surface and an older surface. I subtract the older surface away. And what I'm left with is this output here on the bottom, this what we call GCD, or geomorphic change detection output. Another word for that is topographic differencing. Where the blue is, that means there's been a rise in the surface since from the old time step to the new time step. There's been deposition. Where there's red, that means there's been removal of a surface layer. So we care about sediment budgeting in this example. So we're looking at how much sediment is being moved up and over this dune system, how much the beach is eroding, all these different changes to try and quantify, in this case, a restoration project. Here, this is a little bit different. This is a vegetation surface that we're looking at. So on the top, that's August 2021. That's a digital elevation model of that same beach dune system from August of 2021. Below that, that is the elevation model, or the relative height of vegetation over that same beach area in August of 2021. And the bottom one is telling us how much biomass and volumetrics that vegetation is taking up. So here we were able to quantify pretty accurately, or at least to a decent degree, the differences in vegetation cover over this beach dune system that had been restored. And we cared about how well the vegetation was doing, where it was growing, how much it was covering, etc. So we did this, and we made these calculations and did these estimations and came up with this. This is a geomorphic change detection surfaces from November of 2015 all the way through September of 2021. There's a lot of changes that we're recording here. We're out there almost two times to more a year since 2015, and just reconstructing and rendering these beach and dune systems. So we've looked at this now for nearly 7 years. Again, as I said, we went out in July of 2022 this year. And if you see in the bottom there, if you're interested in learning all about this stuff, that's an article I published very recently, July 6th of 2022. Dynamic restoration and the impact of native versus invasive vegetation on coastal Florida morphodynamics, Landford Dunes, California, USA. That is one of the big chapters out of my dissertation, and something I think we're really passionate about getting out there, looking at how this beach dune system has changed using a terrestrial laser scanner for a pretty decent amount of time. This type of high resolution focus on beach dune restoration really hasn't been done to this degree yet. So we're really, really excited to get this out there. If you're interested, reach out. I would be happy to pass this along. I'm sure Dr. Rosario would also pass that along if you ask. So just reach out or stop by Phillips 253, and I'm happy to get that to you. Some other potential applications, cultural mapping. This is a really cool one. So what we're looking at here is this is from Wisconsin, and this is a effigy mounds that have been identified with LiDAR. Native American effigy mounds, and you see them along this river corridor here. They build it on the terraces above the river. Rivers are thoroughfares for the people that live there, sources of food, sources of water. a way to travel quickly up and down. Their effigy mounds surround these. So we're actually looking at birds, quadrupeds, other different types of effigies that were all identified using an aerial LiDAR scan here. And you can find it in that Beaujart et al. 2018 article. I'd be happy to pass that along. And you can see in that top one here, it's a little tough to make out, but there might be a quadruped, a bird, a snake, all sorts of things that you can actually see. That's one of the big things you might have heard recently, aerial LiDAR being used in Peru to find Aztec ruins in the rainforest. These are giving us unprecedented opportunities to find things of cultural interest. It's really fascinating stuff. You can use it for historical documentation. So this slide, make sure I acknowledge this. I got this from a presentation from Dr. Karen Gran at University of Minnesota Duluth. Fantastic scientist. Definitely look into her work. She's done a lot with LiDAR in Mount Pinatubo, the Blue Earth Lusur River of Minnesota, in the Duluth area. Give it a look. Give her a look if you're interested in that type of work. So here, she was giving a presentation and had these included. This was laser scans of this historic bridge, the Roseman Bridge in Madison County, Iowa. And they were basically trying to document this and render it for people to see and experience in 3 dimensions, maybe from the comfort of their own home if they weren't able to get here, but also to keep this preserved in this point cloud format. The moai on Easter Island have been scanned for cultural preservation, trying to understand maybe where they're deteriorating, what they look like, how much space they take up. Just really fascinating work. This was from an article by Kirsten et al. In 2010, where they scanned these moai in. Use it for cultural preservation and forensics as well. Here, from Vivant et al. 2014, they were looking at the terracotta warriors of China and scanning them and looking at the intricacies, their ears even, it's very fascinating work that they were doing, trying to preserve and understand the terracotta warriors. So LiDAR has a kind of unquantifiable array of different things it can be used for. This is only some of the ones I've used, or I've mentioned here. It can be used for crime scene preservation, where they'll go out and they'll scan a crime scene after for example, an accident happened. They'll go scan it with a LiDAR system, so that they can go back and see with incredible detail where things were, explore the scene in point cloud format. You can use it for things like archaeological dig site reconstructions. So if you want to go back and look at things in your archaeological digs, GeoArc people use it all the time. And I've only touched on some of the applications as far as the volumetrics. People use these for glaciers and monitoring mass balances on glaciers. So LiDAR is just one of the coolest tools that we have at our disposal right now. And as it gets more accessible and cheaper, the extent and distribution of data sets that we have is only going to increase. On that note, where can you find LiDAR? Well, the first and biggest source that I would push is Open Topography. This is an NSF, or National Science Foundation funded organization. Some of my old colleagues at Arizona State University were some of the founders of Open Topography. And what this is basically an extensive data sets that are either from the Open Topography crew, the United States Geological 3DEP program, community data sets, or global and regional DEMs. So you can go in there and find an array of systems that have been uploaded and preserved here. You can see there are some throughout Minnesota, Wisconsin, Michigan, Iowa, Indiana, Illinois, all over there, all over coastal California, if you want to see that. I think Mount St. Helens and some of the mountains in Washington and Oregon are in there. And I just have it focused on the United States, because you can go outside the US, and New Zealand is done ad nauseum, or ad kind of, there are so many data sets from New Zealand that are just mind-blowing to look at. You can just download all of these for free. You just have to sign in and you can download these data sets. Outside of Open Topography, you can go to that USGS website I have posted here. The NOAA Data Access Viewer is another phenomenal one for coastal-based data sets, because that's the National Oceanic and Atmospheric Administration. That's their bread and butter. For Wisconsin-based LiDAR, you can go to the State Cartography Office to find their digital elevation data. For Minnesota, you can go to Mintopo is the site that you want to go to there. That's run by the DNR. Or you can just Google it. Look for LiDAR where you're interested, and it could be based in a county, it could be based somewhere else, but you can find those data sets if you're interested. Or if you think there's LiDAR and you're not sure where to find it, reach out to me, because I have made it a habit of if it exists, I'll find it. And if I can get access to it, I will. So absolutely willing to help you out. If you need that help for your remote sensing projects, feel free to reach out. Or if you're interested in doing further projects, reach out and talk to me. And I want to make sure that I reference, bring to light all of these different sources that I referenced, from Chris Crosby at UNAVCO, Dr. Karen Gran, UMD, these links that I provide here. So there's a lot of really great resources that I use to develop this presentation. So I hope that you enjoyed it. You got to listen to me nerd out for a while. If you have any questions, reach out. If you need to talk to Dr. Rosario, reach out to Dr. Rosario. You can get in touch with me, or you can reach out to me in person, or just stop by my office. So I hope you enjoyed this presentation. I hope you have a great day. Thank you so much.